I'm Ellen Wickstead, and this is the course project for Machine Learning Foundations. The project that we're working on involves adjusting an existing machine learning model that uses ambient environmental readings to predict the hourly energy output for a combined cycle power plant. We've been asked to determine whether we can simplify the current model and further streamline it to make it easier to interpret without compromising the adjusted R-squared values by more than 2%. Let me explain a little bit about the sample data that we're using to work on this project. We've got a sample data set that includes just under 10,000 observations. Each observation includes 4 data features, as well as the dependent variable that we want to predict, which is the net hourly electrical output. You'll see in the spreadsheet a little bit later that that's referred to as PE. The data is structured and the values are continuous, so we are using a multiple regression model as the most efficient approach. It's also one of the easiest machine learning models to interpret. 80% of the sample data will be used for training and validating the updated model, and 20% of the sample data has been set aside for testing the different algorithms. And you can see over on the right-hand side the different data features that we're working with, as well as the ranges that the data shows. So let me explain how we went about answering this question. And we took the approach of adjusting, trying multiple algorithms to see removing which of the 4 variables gave us the best results. So below is a screenshot of the baseline value with all 4 values. And you can see that in this example, all 4 of the first columns, which are the data variables, are highlighted in green. The adjusted R-squared value is 92.82%, and you can see down below that the coefficients for each of the 4 variables. We then made 4 copies of the data set and readjusted the algorithm, reran it, and excluded a different data variable each time. Because each of these 4 new models includes only 3 data features, this allowed us to compare these against the baseline model adjusted R-squared values. And then once we were done with that, we actually ran those 4 algorithms again on the test data so that we could compare the validation results and the test data results for each of the 4 new algorithms. As expected, there were minor differences between the validation and the test data sets, but no major surprises. And just as a reminder, the adjusted R-squared value is widely used as a good indicator of when a model has good predictive accuracy, as it sort of balances the number of variables and their relative impact on the model's overall predictive ability. Let me switch over to Excel so we can take a look at the data. So in this particular example, you can see this is one of the test data examples, and this shows the example where there's no temperature included. So I'm not going to walk through, but we have similar setups, and in this case you can see that the temperature column D is grayed out to indicate that it is not being used in this particular model. And again, this is the test data variant, and I'll show you a slide that shows all 8 of the tests that we ran. 4 algorithms, the validation set, and also the test set. And you can see over here, you can see the coefficients for exhaust vacuum, ambient pressure, and relative humidity. Let's go back over to the PowerPoint and take a look at the different algorithms. So you can see that the first 3 options that we explored, removing ambient pressure, exhaust volume, and relative humidity, all of those meet our criteria for the output value that we were given as sort of the goal of the project. Removing temperature is not an option because that would have a significant negative impact to the model if removed. I'm going to move on to our recommendations. So as I stated in the last slide, we can remove any of the variables from the model except temperature and achieve our goal. Removing ambient pressure is the obvious choice here, but the monitoring equipment used to gather that data is both inexpensive and highly reliable. However, removing exhaust vacuum as a reading from the model um, only compromises the predictive accuracy of the model slightly, but it actually has the potential to remove an operational headache. That sensing equipment is fussy and requires frequent resetting and replacement. So, eliminating this feature from the model has the potential to simplify operations and reduce costs while also making the model easier to interpret. This makes it a good choice for both meeting the output metric goal and delivering a better business outcome. Finally, removing relative humidity from the model is a viable option, but it doesn't provide any benefit over removing either ambient pressure or exhaust vacuum. So that would be sort of our recommendation of last resort. Thanks for your time, and appreciate you taking a review.